The learning target for this lesson that we're looking at is that you can evaluate, analyze, and graph exponential functions. An exponential function is of the following form. F of x equals a times b to the x, where a and b are real numbers. A is not 0, b is greater than 0, and b is not 1. If b were 1, then you really would be doing a number times 1 to a power, and 1 to any power is 1, so then it wouldn't be an exponential function. All right, so we have a couple different things. We're going to be sketching and analyzing graphs. You looked at these in Algebra 1 and in Algebra 2, actually, mostly. Sketching and analyzing the graph of each. Describe its domain, range, intercepts, asymptotes, end behavior, and where the function is increasing or decreasing. So I'm going to ask you to make a table, and you actually probably don't even need your calculator for this if you remember what negative exponents do. What is 3 to the negative second really? What's the negative tell me on an exponent? So it's in the wrong spot, so it's a reciprocal value. It's 1 over 3 squared. So it'd actually be what? 1/9. So you're going to do this for this function, 2 to the x, and your table will go from negative 3 to positive 3. Oh, shoot, I didn't leave enough room to complete your table. And go ahead and graph that. All right. Who can tell me what the table was? Who has their table completed? Yeah.
Can we just read off the y's?
Yeah.
1/8.
Yes.
1/4.
Okay.
1/2. 1, 2, 4, and 8.
Perfect. So your graph should actually look like this. Is it going to have x-intercepts? What do you guys think? If you're not sure, right, 2 to any power, let's do the negative 50th. Depending on what unit of measure you're measuring, that may be 0, you know, in terms of physical quantities. It might not. If you're measuring in certain units, it may not be. It may actually have a physical quantity still. But that is really close to 0, but it's not 0. There is a decimal value for it and a fractional value for it. So it doesn't quite reach a height of 0. It's continuously approaching it. What does that make the x-axis? A what type of one? A horizontal. So we're going to sketch a dashed line for a horizontal asymptote at y equals 0. This is the parent function for all exponential functions with a base of 2. So all functions that, you know, if it was a base of 3, it would be very similar. It would still be 3 to the 0 is 1, but then this would just go up to 3. It would rise a little faster than this one rises. If it were 5 to the x, it would rise even faster. 5 to the first would be at 5. 5 squared would be at 25. But it would still be the same basic function in terms of the sketch of the graph for the parent function. Now, who has a description for the domain for this? Anyone have a description for the domain? You can look at the graph to get it, right? X can be all real numbers, so that's negative infinity to positive infinity. What about the range? Is that also negative infinity to positive infinity?
It's 0. It's 0 with the
So it's 0 with a parenthesis because it can't equal 0. And it goes up infinitely, though. Now, this restriction on the range is going to affect two things. Actually, it becomes from the horizontal asymptote, which I forgot to do intercept, so we'll do that in a second. Comes from the horizontal asymptote being y equals 0. And that's also going to affect our end behavior when we get there. But we're not there yet. So in terms of our intercepts, we don't have any x-intercepts. We do have a y-intercept, which is 0, 1. And unless there has been a vertical stretch or compression or a shift up or down, for all functions that are exponential, the y-intercept will be 0, 1. Unless one of those things has happened. All right, so now, what's this? I don't know if that's even working. There we go. All right. Let's see. The only other thing we have is end behavior, and then describing the increasing or decreasing. End behavior we write in limit notation. Is there a limit on the function as I go left? Is there a limit on the function as I go right? And if not, then it's, okay, I put a line over it again. I'm not sure why. There's not supposed to be a line there. That's supposed to be not negative infinity, so pretend that that's gone. Should be positive infinity. All right, so as I go left, is there a limit, or does it just go down forever? Well, it is decreasing, but is it getting more and more negative in terms of, no. So it doesn't get below 0, so there is actually a limit on it. It goes up to, but not over 0. And then limit on the function as I go to the right, there is no limit. It increases infinitely. And then they also ask for, is this function increasing or decreasing? Well, as the person walks from the left to the right, even if they start way back here, they're going to start walking up just very small increments, very, very small. It will seem like they're walking off flat land, and all of a sudden they'll have to walk straight up that hill. So this is increasing for the entire domain. So negative infinity to positive infinity, and that's how exponential growth works. This one would be considered growth because as we go from left to the right, the values are increasing exponentially. All right, so what I'd like you to do is make a table for this one, and we'll talk about how we can get that using the parent function in a little while. But right now you can just make it on your calculator and graph it, and then see if you can answer the parts that we just answered above. So you can make it on your calculator if you want to for this next one. All right, so this is the table that you should have had. It's a little hard to see, so I'll read it off. Negative 3, 5, negative 2, 1, negative 1, negative 1. The other y values are negative 2, negative 2.5, negative 2.75, negative 2.875. So you could have gotten this from your calculator or by performing transformations based on the original table. I did graph the original function, which you'll see in just a second, and put that in blue and this function in red. It no longer looks like exponential growth. It has the right base, but some things happened to this function that make it look different. Who can tell me what one of the things are that happened to the function? Anybody know? What's up? It does cross the x-axis now, yes. And there's a reason for that, and it's because, okay, that didn't look right, so I'm going to fix that. It's because of this. What happened to every point on the graph because of that? They all shifted down 3 units. So something more happened before that, but then once we had the points, they all shifted down 3 units. So that's why I now have an x-axis. What happened because of this sign on the exponent? Well, I'll tell you, before it shifted down 3, so if I move this point up 1, 2, 3, and this point up 1, 2, 3, this point up 1, 2, 3, it's a reflection over what? Over the y-axis. So we're going to talk about transformations in a minute and how they impact what we expect to be exponential growth. We'll be looking at just graphing next in a minute. So with this, though, we have the same domain and the same range. No, not the same range. The range does go up infinitely, but it's no longer a minimum value of 0. It's a minimum value of negative 3 because everything shifted down 3 units, including the horizontal asymptote. Okay, just like with rational functions, if we had one at 0 and it shifted down because of a minus outside of the fraction, same thing here. If it's minus 3, the horizontal asymptote shifts from the x-axis down to y equals negative 3. If it shifts, if that's a plus 5, then it will shift up 5 units. So this is negative 3 to infinity. There are x-intercepts. You can see them right in your table, and a y-intercept. The x-intercept was... Actually, I don't know if I have it. Did I graph it? Was it negative 1, 0? Negative 1.5. So you used your graphing calculator. Thank you. Negative 1.580. So you could calculate the 0 from that. We have a way to solve it too, but we haven't covered that yet or reviewed that yet. And then we also have 0, negative 2 for the y-intercept. For our horizontal asymptote, we just said that that's what affected our range, so that's y equals negative 3. Our end behavior is a little bit different, the limit on f of x as we go to the left, the limit on f of x as we go to the right. It's going, which one is affected by the horizontal asymptote, left or right? Right. And so that's negative 3. The other one goes up infinitely. So unlike rational functions where the horizontal asymptote affected both end behavior, both parts of the end behavior, for exponential it will only affect one side of it, the horizontal asymptote. As our person walks from left from right, the function is decreasing very fast at first and then so small in increments that it's almost like they're walking on flat ground, but they're not. So this is decreasing over the entire domain of negative infinity to positive infinity. All right, we're going to review general rules of transformations and then look at how they apply to these functions in particular. The rule for transformation is f of x. Normally there's some type of function involving x. There should be a little space there if I tried to leave a little bit more there. We have a and k outside of the function that are going to do stuff to the function, but they're really outside of the function initially. And we have b that's multiplied with the variable x, and h. I probably wanted to use different colors than red, but that's okay. So the reflection, we already know, we said b, if b is negative, so if b is less than 0, if b is negative, then it's a reflection across the y-axis. What happens if a is negative? Anyone remember? It's a reflection across the x-axis. Correct. So if you see that in a function, you'll know to expect that on your graph, that's going to happen to your graph. Stretches and compressions also come from a and b. If a, and we're going to talk about the absolute value of a because we're going to ignore the sign on it. If the absolute value of a, so just pretend a is positive, doesn't matter whether it's a positive or negative, that the negative only affects the reflection, is greater than 1. So it could still be a fraction like 5/2, but 5/2 is bigger than 1. So if it's bigger than 1, then it will be a vertical stretch by a scale factor of a. So let's say it was a 3, then it would be a vertical stretch of 3. Or a vertical, not by, but of, a vertical stretch of 3 of a. If the absolute value of a, again, we're just looking at the numbers, not worrying about the sign. So if it's a fraction that is less than 1, so I guess I don't need the whole greater than 0 if I have absolute value, because absolute value is always positive, but this would be a vertical compression of a. So that means, hey, our fraction is 1/4. Well, then it's a vertical compression of 1/4. All the points, whatever their height was before, It'll be 1/4 of what it was previously for the parent function. For our for the value of b. So before I do that, I want to talk about translations, and I'll come back to that. So translations, if I see plus k, what does that mean? If I saw plus 4 out here, what happens to all the points? They all shift up k units. And if it's minus k, then it's down k units. Whereas if I see minus 4 in the parentheses, does anyone remember what happens? Which way does it shift? Somebody said it. It shifts right, and that's right. If you see minus the number in here, it actually shifts right. You're thinking, well, it's negative, so it's going to shift left, but it doesn't. We've seen it time and again that it doesn't. So that is a shift right. It's counterintuitive. And if we see plus a number in those parentheses, then that's actually a shift of left. Again, counterintuitive from what we see with the sign. H is not the only thing that's counterintuitive. Anything that's inside of those parentheses, including b, is counterintuitive. So if the absolute value of b is greater than 1, we're thinking, hey, that's a 5. I'm expecting it to be 5 times as big. But it's not. It's actually the reciprocal value. Instead of being 5 times as big, it's 1/5 of what it was. Because if this is the case, then it is a horizontal compression of 1 over b, the reciprocal value of the number that you see in front of x. Everything inside that happens inside of the function that happens to x directly is counterintuitive to what we see. So if I have the absolute value of b is less than 1, so now I have a fraction, a number between 0 and 1, then even though I see that fraction of 1/2 and think, oh, it's going to be half the size it was, it's counterintuitive when it's horizontal. So that's actually a horizontal stretch of 1 over b. So if my fraction was 1/2, it'll be a horizontal stretch of 2 over 1. So these are rules for transformations, which you guys should have had in Algebra 2. You guys kind of remember that a little bit? Okay. So I'll leave that up for a second, and then we're going to go to the next side. And we're actually going to, instead of generating a whole new table, we're going to take the table of our parent function and just make some minor changes to it to get our new graph. Does anyone still need that up there? You guys all set on this side? Alrighty. So example 2, graphing transformations of exponential functions. Use the graph of the parent function. In this case, I picked 2 to the x. I could have been 3 to the x or 5 to the x. To describe the transformation that results in each function, then sketch the graphs of the functions. So for my parent function, I'm going to use the same table for all of these graphs. This will be my f of x, my parent function, 2 to the x. We generated this table on the other page, so I'm just going to give it to you already. It's 1/8, 1/4, 1/2, 1, 2, 4, 8. So this is our parent function. And we're going to sketch that on all of these, but we'll do that as we get to each graph. On the other side, I did want to make one brief note, and that is which one of these happens to the y? Which one of these letters here affect the y coordinate? A, right, because it's a vertical stretch. What else? K, because it's up or down. And then B and H affect the x coordinate. A affects it through multiplication. K affects it through addition and subtraction. B affects it through multiplication of the reciprocal. H affects it from addition of the opposite of what you see. For our function 2 to the x, our exponential functions, this is what our transformations look like. A times, here's where it gets confusing. I'm going to do capital B for the base because every exponential function has a base and that's not part of our transformation. To the power of bx minus h plus k outside of or down below. So a and k affect the y coordinate. If I start with a point xy, which is what I have in my function for my parent table, an xy coordinate, the x coordinate changes by the reciprocal of b. So it'd be 1 over b times x plus the opposite of whatever h is. Because again, it's counterintuitive. If you see minus 3 there, I'm not going to subtract 3, I'm going to add 3. For the y coordinate, well, that should be a comma, not a parenthesis. For the y coordinate, I'm going to multiply that by a and add k to it. To get my new ordered pairs from the transformations. So as I look at this function, yes? So I'm just saying that this is, we said that this is what affects the x coordinate, right? Because it's a compression or a stretch, a horizontal one, and then it shifts the whole graph left or right. So if I'm going to compress horizontally or stretch horizontally or shift left or shift right, that changes the x coordinate. So this multiplier, take the reciprocal, multiply it by x, that'll give you the effect of the compression or stretch. Take the number that I see in here, like if it's positive 3, I'm going to add negative 3 to it and shift it left 3. Then for this, if it's a vertical stretch of 2, I'm going to multiply the y by 2. That'll make the points twice as high as they were before. And then if it's a shift up of 1, I'm going to add 1 to it to shift everything up 1 unit.
So A like stretches it?
Vertically, yes. A either stretches it vertically or compresses it if it's a fraction less than 1.
Okay.
Yep. So for this function, I'm going to describe the transformation, and I'm only going to change this graph or one of these columns slightly. What does x plus 1 in the exponent mean? What happens to the graph? It shifted left 1 unit. So here's the cool thing. If I'm going to do the table first, but that affects my x value, so my y will stay the same. My y is still 1/8, 1/4, 1/2, 1, 2, 4, and 8. I don't have to recalculate those. My x coordinate just shifted left 1, so it's x minus 1. Even though it's a plus 1 here, it's left 1, so it's x minus 1. X plus the opposite of whatever sign I see there. So this is negative 3 plus 1, or sorry, it's negative 3 minus 1, negative 3 minus 2. So all of these just shifted left 1 unit. So my new table, I don't even need my calculator to generate. And honestly, I don't even need really to do this table if I had plotted the original function. The original function was, I'm plotting the original 0, 1, 1, 2, 2, 4, 3, 8. Then I had 1/2, 1/4, 1/8. And so I have this as my parent function. This is my f of x. See, it says graphs of the functions, plural. So there's my parent function. Now I'm going to graph g of x, which has shifted left 1 unit. I honestly don't even have to follow the table. I can just take these points and move them left 1 unit for each one of them. It's a little dicey over here because of the horizontal asymptote. They're kind of going to just kind of blend together because it's such a small, because it's going down in small, very small increments. But the rest of it will look pretty parallel, except not quite as it gets closer and closer to that horizontal asymptote. And that's g of x, so I'll label that one g of x. What's going to happen in letter B? You guys see this negative exponent? What does that mean? What happens? Well, it does affect, it is b. So b is usually reciprocal, but that's if it's a number, but it's just a negative there. So it's going to be a reflection, right? Over which one? Over the y-axis. So the cool part is, if you know that that's all that happens, you really don't have to generate a whole new table for it. You just graph the parent function and reflect it. But if I were generating this, that changes the x coordinate. It's the opposite of what it was before. So in this case, my new table, this will be my g of x, is going to have the opposite x value than what it had before. So now it's going to be 3, 2, 1, 0, negative 1, negative 2, negative 3. I just took these and changed the sign on them. The y values, nothing happened to the y because there's no value for a is 1, and there's no value for k is 0. So I've got 1/8, 1/4, it stays the same as it was before. So I'm going to plot my original function in blue, 0, 1, 1, 2, 2, 4, 3, 8, 1/2, 1/4, 1/8. Here's my sketch of my original function f of x. I'm going to do the g of x in red, and I can either follow the table or I could literally reflect these points across, oh no, not the x, across the y-axis. Bless you. So I can clearly see they have the same horizontal asymptote, but one, because of that negative now, looks more like, is more of a decreasing exponential function. Started as an increasing, but the reflection makes it decreasing as I go from left to right. Questions on that? All right, see if you can make or describe the, no, I'm going to do this one with you, and then you're going to do this last one, sorry. For letter C, we have multiple things going on, but none of them are happening to x, which is nice. What's happening here and here? There's actually, how many things are happening? It looks like 2, right? So the +4 is easy. What's that do to the graph? Shifts it up 4. That's the last thing that happens to it, though, because order of operations tells us to multiply by the -3 first. The 3 part tells us that it is a vertical stretch of 3. What's the negative do? A reflection across the x-axis. So I could take my points and reflect them across the x-axis, make them 3 times as far as they were before, or as large as they were before, and then shift them up 4. That seems like a lot of work. If it was just reflection or just 3 times as much, I might do that to my individual points, but there's a lot more going on. So I'm going to actually use my table, but I'm going to start from my original table. So I'm going to plot the original function first, 0, 1, 1, 2, 2, 4, 3, 8, 1/2, 1/4, 1/8. There's the f of x that we're supposed to compare this to. Now I'm going to make my table. See if you can figure out what we're going to do to x, the x coordinate, and what we're going to do to the y coordinate. Take a second to discuss that with people at your table. See if you can agree on what we're going to do to the x coordinate and what we're going to do to the y coordinate from our original table. All right. Mr. No. Let me see. Who else can I pick on? Carter, what variable are these changes going to impact? The x or y coordinate? The y coordinate. So I'm going to keep my x's since nothing happened in the exponent. Nothing happened to x. So that means b is 1 and h is 0. I don't have to change anything about my x coordinate. I'm going to keep the x coordinates exactly as they were. But my new y coordinate, what am I going to do to the old y coordinate? Multiply it by what? By -3, and then add 4 to it. So I have 1/8 times -3, that's -3/8. So I'm just -3/8 plus 4 is 3.625. Multiplying this by -3 is going to be -3/4 plus 4, which is 3.25. Multiplying -1 by multiplying 1/2 by -3 is -3/2 plus 4 is 2.5. 1 times -3 is -3 plus 4 is 1. 2 times -3 is -6 plus 4 is -2. 4 times negative 3 is negative 12, plus 4 is negative 8. And negative 3 times 8 is negative 24, plus 4 is negative 20, so we're not going to be able to plot that, at least on this graph. So we can now plot these points. We have negative 3, or positive 3.625, negative 2, positive 3.25, negative 1, 2.5, zero, 1, 1, negative 2, 2, negative 8. I feel like I messed something up here. Just double check something. No, that's right. So this is curving down this way. What value is it never going to reach? Look at the equation. What value is it never going to reach? 4. Because it would have been the horizontal asymptote at 0. That was our parent function's horizontal asymptote. But this whole graph shifted up 4 units, including the horizontal asymptote. So this line will get close to it, but it's never going to hit it for these types of horizontal asymptotes. It can for the rational equations sometimes. So there's our graph. Try this for letter D. See if you can, this table should be even easier to generate from our parent functions table. If you can, see if you can say what transformations are going to happen and quickly generate the table to get a sketch of the graph. Who can tell me what transformations happen? What's this negative do? It's going to reflect across the x-axis. So I could actually, this isn't too bad. I could do that easily without a table. And then what's the negative 3 do? Shifts everything down 3. So I could reflect the point and then go down 1, 2, 3. Reflect the point and go down 1, 2, 3. Same thing, reflect, so that's 4. It's a little complicated, but 1, 2, 3, it's not too bad. Reflect the point, I'm not going to be able to go down 3 unless I, because it would have been at negative 8, I'd have to go down 1, 2, I'd have to go to negative 11. And my vertical or horizontal asymptote is now at negative 3. So I can actually get the sketch of this graph really fast, even without a table. I could also use the fact that I'm going to change the sign on my y-coordinate and take 3 away from it, giving me the following: negative 3.125, negative 3.25, negative 3.5, negative 4, negative 5, negative 7, and negative 11. So I can get it that way as well. But I should be able to describe the transformation. In some cases, just use it to change the points, and other times just look at my table, but absolutely be able to describe the transformation. Any questions on graphing transformations of exponential functions? All right, real quick, we're gonna go over these, and you might not be too surprised. The exponential growth, as long as we haven't done any changes to the function, so we haven't done any stretches or compressions or reflections or any of that. If b is greater than 1, so that means that it is a number like 2 or 5 halves or something like that, it's going to be exponential growth. As your guy walks from left to right, it's going to be going up. But if the value for the base of the exponential function is a fraction, then you're going to be going down as you go from left to right. But either way, your domain is negative infinity to positive infinity. There are no interruptions in our domain. Because there are no interruptions to our domain, like a vertical asymptote or a jump when we have piecewise functions, or there's something else. Oh, holes, a hole in the graph. This, when they ask about continuity, this is a continuous function. It has outputs for every value of x you could put in, from any value going left to any value right. So if both of these are continuous functions, there's no interruptions in the domain. So that's when they're asking about continuity, they're talking about are there any interruptions in the domain that would make it a discontinuous function. The range for this one, actually for both of these functions, since nothing has happened in terms of transformations, the range is going to be from 0, but not including it, up to infinity for both functions. It changes when we do transformations. The y-intercept for every parent function, whether it's exponential growth or exponential decay, is 0, 1, because anything to the power of 0 is 1. The x-intercept, as long as it's the parent function for either of these, there is none. If it shifts down or if there's a reflection over the x-axis, then there will be an x-intercept. There are no extrema for exponential functions because there's no max or min value. The asymptote for the parent function, regardless of whether it's exponential growth or exponential decay, is y equals 0. We all know that that will change if the function is shifted up or down. And the end behavior, this is where it differs. They both start out the same, the limit on f of x, just like every function. As x approaches negative infinity, the limit on f of x as x approaches infinity. Here's where these functions differ. As I go to the right on this one, what's happening to the function? It's increasing infinitely. So there really isn't a limit. It's just going to, I just put infinity there because it's increasing infinitely. That happens for the decay function where? As you go to the left. Yep. And as I go to the left on the growth function, it approaches that horizontal asymptote of 0. Now, if our horizontal asymptote has shifted because the graph shifted up or down, that value will change. And for the decay model, as I go to the right, it approaches that. So for any function that I give you that is an exponential function, you should be able to find these things. This is what it looks like for the parent function. The asymptote, the end behavior can change if it shifts up or down. Some of these other things can change slightly, the y-intercept and x-intercepts. Nash, did you have a question?
Yeah, on the end behavior for exponential decay,
Yes.
would it be infinity or would it be negative infinity on the left?
So as I go to the left, it's going up infinitely.
Okay.
So the height continues to go up. So they have the same range, so it's going to be those, but it's what happens as I'm going left versus what happens as I'm going right on the graph. Okay. Our first assignment isn't very much. It is page, hold on, I have it written down, I gotta find it. 166, 1 through 15 odd. It's not a lot of problems. You could start them in class and get help if you need. I have graph paper over there. If you didn't already pick some up, you'll want to pick up a sheet or two, pick up as much as you need for sketching the graphs. But you want to practice this and make sure, especially in the ones that ask, that you can provide this information even after transformations have happened. Okay, that concludes day 1 of our 3.1 notes.